The next topic will be vehicular communications. So those of you who have attended regularly our Beyond 5G forum as well as our research reviews, we typically have a session on this very important topic because we have a very active program going on in smart transportation, also sponsored by Honda Research Institute, which Dr. Eshan Moradi Pari will be giving us a talk on vehicular communications. And a couple of things to mention about him. He leads the Network Intelligence Initiative at Honda Research Institute. And he is very, very active in all the relevant organizations, including, as you know, 5GA, CAMP, very knowledgeable in that field. So we'd like to welcome him to give a perspective. Also, he'll be talking about both safety as well as, I'll sort of let you. Thank you.
Hi, everyone. It's my honor to be here. My name is Eshan, and I'm the lead scientist for Honda Research Institute. I will talk about the vehicular communication evolution the past decade, from active safety towards more a harmonious environment and harmonious mobility and driving. So I would like to introduce a new kind of aspect to this forum. So first, Honda Research Institute. You all know Honda, but Honda Research Institute, we are part of the Honda Group. It's a global network. We have offices in United States, Europe, in Germany, and in Japan. And in United States, we have 2 offices. Our slogan is Innovate Through Science. We conduct computer science, material science, and mobility research. The Silicon Valley office is the headquarters, and we have an office for a good reason in Detroit area in Ann Arbor because of closeness to automotive industry, and Silicon Valley close to tech industry. My background, I'm wireless. I come from a wireless background, and network intelligence department is the group I lead. This is a kind of a roadmap of what we conduct research, where we started and where we are heading. So we first started from the generation 1, we called it. It's about detecting some abnormal driving behaviors, such as like someone is tailgating someone else, how to prevent such situation. Generation 2, it was when we discussed about making prediction using over-the-air information to making some prediction and predicting behavior of other road users and having some proactive decision makings to prevent conflict. That was generation 2. And generation 3, it's more cooperative planning through synchronization. Imagine a scenario that you want to merge a main traffic on a highway, how you can negotiate with the main traffic flow to have a more smooth joining the flow. In some areas, such as Los Angeles, it's not easy to join. In Detroit, it's the same. So it's a battle, kind of. So how to leverage technology to negotiate joining smoothly. And we expanded that not only for highway to more urban environment. And as you know better than me, the first challenge is the diversity of the road users. It's not only cars. You have pedestrians, you have elderly citizens, you have, these days we have many of these micro devices, such as electric scooters and also e-bikes. Also, delivery robots, they're coming, drones, they will be there. So how to create a harmonious environment, having all of these, that's the topic of our research. The end goal is a cooperative mobility, risk-free, stress-free, and anxiety-free. First, I introduce a kind of history of direct communication and how it was used for automotive industry. It was 1999 that FCC allocated the spectrum. As our keynote speaker first introduced, the first thing we discussed is the spectrum. So FCC allocated spectrum for automotive safety. It was a 5.9 gigahertz spectrum. It was a 75 megahertz for V2V and V2I. After that, a group of OEM, they started to work on things that matters for deployment, such as interoperability. We all speak on the same language. We as Honda don't speak Japanese versus GM speak English. So we wanted to create standards, as well as we wanted to discuss some of the other issues, such as congestion mitigation, because you living in California, you know how congested sometimes the road can get, and the system has to operate. Then it was a grant to City of Ann Arbor by US DOT to create a connected vehicle environment, the first pilot projects. After that, Wi-Fi industry asked FCC for a spectrum in that specific band that we were operating. Obama administration put a notice for rulemaking regarding these active safety system and use of V2V for safety. But later there was election, administration change. This pre-regulation was put on pause. And then there was other technologies also introduced, such as CV2X, the same, delivering the same features, but just a different chipset. There were announcements from OEMs, right and left, but then FCC chopped the spectrum. And the spectrum, it was 75. FCC reallocated a lower portion of it to Wi-Fi, and we ended up with 30 megahertz only for V2X, and it's a CV2X spectrum now. So first of all, what is the role of these type of communications? We have onboard sensors, we have camera radars, but those, they can cover up to 100 meters, and they are for collision avoidance. Up to 100 meters if the view is not blocked. If you are at intersection, there is a building, you cannot see the other side, you cannot see the cross traffic. Also, we have cellular technology for telematic system. Of course, they provide some sort of awareness about traffic situation, and they're more used for infotainment as well. We wanted to leverage this wireless technology, these dedicated technology, direct communication, to fill the gap between these two, to expand the sensor range, because they are limited, especially if the view is obstructed. Also, we wanted to expand it to 1 kilometer and provide some sort of warning to driver, hey, something will be coming up if you continue this way. This type of information for driver. There is someone behind the building that approaching you that your sensor can't see. This type of, please watch out for that, and this type of information. It was a 360 view, including non-line of sight. It was good for, at any situation, good for up to 300 meters. If there is no building, if the view is not obstructed, it goes above kilometer. But it depends on the fading environment and the things that you know better than me. But this was purposed for these type of warning the driver or advising the automated system to take some action pre-collision or pre-hazard situation. Okay, so yeah, in this slide, I wanted to show some of the applications. I have a better slide after this, which is a video that explains some of the most advanced application of these. But the typical application were V2V, V2I applications like do not pass warning, emergency brake, someone ahead of you have a hard brake, maybe there is an object on the roadways or other reasons, for any reason. Or intersection level infrastructure to vehicle were more like about the traffic light information. If someone is running a red light, or work zone in the area that the workers are working, safety of the workers is important, and those type of kind of application were the early application of these V2V, V2I system. The two technology I mentioned, the first one, it was dedicated short-range communication, or DSRC. The second one that came after that was CV2X, LTE V2X. And as you know, it has to operate in a congested environment, and it should deliver a good quality of service under those. So that's very important for us. Here I have some of the scenario that we developed. They're real-world scenario. We developed them under Smart Mobility Corridor project. If you search it, 33 Mobility Corridor, it shows up on internet.
Head-up display informs the driver that other connected vehicles are also on the road. The situational awareness application displays the relative position of other connected vehicles and connected pedestrians near the driver. Signal countdown timer. As a vehicle approaches a connected intersection, the driver receives a red light countdown, allowing the driver to adjust the vehicle speed to cross the intersection when the traffic signal turns green. Maintaining a steady speed with fewer stops can improve energy efficiency. Lane speed monitoring. On the Smart Mobility Corridor, the network of connected vehicles is mapped to indicate the traffic flow for each lane. The lane speed monitor allows the driver to select the lane with the least congestion, saving some time and energy. Sudden braking alert. An obstacle on the road causes drivers to begin hard braking to avoid a collision. Connected vehicles closest to the obstacle communicate a warning to approaching vehicles, allowing them to slow down gradually and reduce the potential for a collision with other vehicles. All connected vehicles within the communication range receive the alert with no direct line of sight needed. Honda Parking Finder. As the Honda connected vehicle passes through the guard shack, the Parking Finder application provides information about the parking layout.
Hard parking.
As the vehicle gets closer to the parking, it recommends an available parking lane closer to the building entrance.
Available spots in lane 7, proceed to parking lot and then keep left.
Once in the parking lanes, more detailed availability to the left and right is communicated. The Parking Finder application sends updated parking availability every 30 seconds. With this information, connected vehicle drivers may save time and more efficiently find available parking.
Okay, this technology, this group of technology, we call them safe swarm. As you can tell, it relies on other road users to send some information to the car, and it makes some determination using those information. But what is wrong with, what is missing in this current status of this? The first thing is that the available spectrum is not enough. We have 30 megahertz, and it cannot cover all the road users. Another issue maybe is that safety of pedestrian is very important, but we do not have such handheld devices today that they can use, that they have the direct communication capability inside them, and they can talk to the cars. So that's also missing. Also, this system is relying on others to talk to you. We need a good percentage of the road users to be able to talk to each other to realize all this. Also, as you can tell, there is still some hardware requirement, which is okay for cars. We have room to add hardwares, but for motorcycle or for some of these smaller mobility solutions, they don't have much room to introduce hardware to do such thing and add some computation capability to those. So that's also another challenge. Then we started the 5G research when 5G came. I show you a video first of the collaboration we had with Verizon at University of Michigan, test track. It's called M-City, and then I will continue.
Honda and Verizon have teamed up to research new connected safety technology that has the potential to reduce collisions and save lives. Since 2017, Honda has been developing safe swarm technology to realize a collision-free society. Using vehicle-to-everything V2X communication, Honda's Safe Swarm could enable vehicles to communicate with other road users and share key information such as location and speed. Now, Honda is collaborating with Verizon to research the use of 5G technology for connected and autonomous vehicles. 5G wireless technology has the potential to ensure fast, reliable communication among vehicles, road infrastructure, pedestrians, and motorcycles. 5G technology allows auto OEMs to move the artificial intelligence from the vehicle to the mobile edge compute, MEC, reducing the need for AI on board each vehicle. Honda and Verizon recently demonstrated their joint safety research at M-City, a connected and autonomous test facility in Ann Arbor, Michigan. Superfast data transmission is essential for connected vehicle safety. Using Verizon's 5G ultra-wideband, mobile edge computing, and the V2X software platform, Honda and Verizon demonstrated 3 safety scenarios. A pedestrian is crossing the street at an intersection. An approaching driver cannot see the pedestrian due to a building obstructing the view. Smart cameras mounted in the intersection relay information to MEC using the 5G network. MEC detects the pedestrian and vehicle, determines the precise location of road users, and sends a warning message alerting the driver of the potential danger. A driver cannot see an approaching emergency vehicle and cannot hear its siren due to the high volume of in-vehicle audio. MEC receives a safety message from the emergency vehicle and sends a warning message to nearby vehicles. The driver receives a visual warning. A vehicle fails to stop at a red light. Using data from the smart cameras, MEC detects the vehicle and sends a red light runner warning message to other vehicles approaching the intersection. These safety scenarios demonstrate the potential of fast, reliable 5G to communicate urgent safety messages between vehicles and infrastructure, reducing the need for complex computing on board each connected vehicle. In the future, connected vehicle technology can help ensure that autonomous vehicles will be able to communicate seamlessly. Honda and Verizon hope their research collaboration will reduce collisions and save lives.
Okay, the background, as I explained before that, the direct communication is not, there is not much certainty about it. Knowing the spectrum is chopped, also the production planning and all having the required penetration rate that we call, that number of cars on the road connected using this technology is not there. So 5G came and we leveraged the key aspect of it, specifically the fast, high reliable and high throughput communication, and also mobile edge compute and edge computing. So we leveraged that to fill the gap, also enhance some of the infrastructure detection, as well as share some of the computation burden between the cars and motorcycle and the infrastructure. So we tried multiple use cases, including the collective perceptions, which they're not easy to do using the direct communication. We had object level sharing information between the cars. Also, we had the raw data sharing and having the MEC process the sensor data and then distribute the results. They work well at the test track and a smaller setup, but there are challenges associated with this. The first one is how scalable is this system? Of course it works for 2 cars, 10 cars at a test track or other places, but how this solution is scalable to a nationwide deployment? There is still limited coverage nowadays on roadways with cellular communication. There is still a stretch of the road that your cell phone doesn't work because there is no network coverage, and these rely on the network. So what happens to those use cases? Also, MEC optimization, deployment optimization is another challenge. The closer the MEC is to the edge of the road, the better, but how feasible is that? That's also needs to be studied. The carrier handoff, of course, there are solutions for it, but for such mission-critical application, it still needs to be researched on. Also, the local and regional trust establishment is also very important. These are all new technologies, how to get cities and the counties to understand this and come to the table to deploy such system. That's also another challenge. Then the next question would be, why 6G? I think that's to the interest of this group. First of all, the top portion of the roadmap, if you look at those complex scenarios, they include mixed traffic, and they have AI agents that it needs to interact with the car, and cars needs to interact with that. Other road users needs to interact. And also, it was explained, the extended reality, digital replica, driverless cars, mobile robotic, they all require ultra high data rate exchange between them for situational awareness. The current data exchange, maybe it's not the most efficient when it comes to scale it. Maybe we need a better technologies, especially the one that we recently started to focus on is the AI, embedded AI technologies and the neural phi for high mobile road users. Maybe those could be. I have an example of like federated learning setup in robotic that maybe can leverage from this. And there were some initial progresses introduced by 5G, but we expect these initial and baby steps to become giant leaps under 6G. As a summary, automotive and robotic applications, these have been expanded drastically the past decade, from active safety to more harmony on the roads. And we don't have enough spectrum to do that under direct communication. 5G introduced some good capabilities as well as the computation capability and the fact that we can share some of the computation burden with the network. But those were still not to the level that we can deploy it nationwide, and we expect 6G to handle that. And it's not about what we did, it's about what you guys can do for us. So we expect you guys to drive the core science behind 6G and to make all these use cases realizable in future. And I would like to encourage everyone, let's work together to make that happen. Thank you very much for your attention, for your time, and I would be happy to take questions. Thank you.
Thank you very much. Questions?
Yes.
Thank you,
Your
Eshan.
mic there also,
okay.
Gabriel. No.
It's okay? Sorry. Yeah. Yeah, thank you, Eshan. You know me?
Yes,
Okay.
we parked together.
Yes, yeah. So, very interesting presentation. There's one case here which concern me about is the red light running.
Yes.
Those are very short time
Yes.
warning.
Yes.
Do you have the specification for latency at the network? You are talking about from the network right down to the vehicle.
Yes.
What
Yes.
kind of latency requirement?
Yes.
Do you have the spec?
Yes, we do have the spec for those, and for many of these safety, the latency that we expect, well, the latency is one thing. There is something that we think that's even more than latency important, which is, we call it information age, basically. It's like how old is the information we get. Of course, latency is a portion of it, but the network congestion and other aspect, they introduce some other factor to it. But yeah, we have that for these safety. We expect millisecond latencies for information to arrive and to be able to deliver these type of features. Of course, some of them are more complicated, especially the ones that they are on the corridors, because the vehicles, they tend to have a higher speed compared to the urban environment or maybe downtown areas. But yeah, there is such kind of documents that a group of OEM together, we developed that. And I can point you to the website to get those. Yes.
Thank you.
Thank you.
Good morning. So today, every car is a fortress by itself. It doesn't talk to any other cars, and they have radars and cameras and so on and so forth, mostly because the other cars are not equipped to talk to each other.
That's true.
Now, in the future, of course, everybody wants to go into this cooperative model, which is a great idea. And we've seen talks from Qualcomm and others where your cell phone can also talk to the car and say, I am here, and I'm crossing the street and this and that. But there is a presumption that then everybody has it. Otherwise, you still have to be a fortress by yourself in order to not to hit a pedestrian or a bicyclist or a child who doesn't have a cell phone or doesn't have this, or an old car. Like, what do we do with all the old cars?
Yes.
So in a sense, my question is that, well, we always have to rely on what we have today.
Yes.
So when will this, and what we have today is reasonable. I'm not saying it's perfect, but it's decently good. So when will this, in your opinion, be, be rolled on a vast scale so that it can, take
Yes.
us to the next step?
That's a very good question, and I think that's what in the presentation I was calling as a penetration rate. That has been a major challenge of V2X deployment because we cannot get all these at once. It's not a switch that you flip it, okay, from today everything is working. And also there is other challenges with that. We were hoping for a mandate on these technology to be mandated in the cars by government. Maybe that was a better solution. Of course, there will be a phase in or phase out period for the older legacy cars to phase out, but that didn't go through. So it became on industry decision making, and it's hard to get a group of car OEMs to have the same product planning kind of scheme because it's a buy-in. It's everyone has to contribute to this environment. It's not only Honda deciding to do that. Honda and GM decide to do that. No, it's not working that way. Everyone has to do it. But as you said, that's why we started to look at the network solutions, maybe because many of the legacy cars, they do have the network and they do have like 4G or LTE. We were thinking of how we can leverage such kind of information to deliver for the new car until the old cars phase out. That was the only solution we had. And for pedestrian, leverage infrastructure. Not everyone has such cell phone. There is no such cell phone, but even in future, there is, as you said, child, they might not have. We were hoping that on critical environments, such as the urban intersection in downtown and things like that, we leverage the cameras mounted at the intersection, and some edge computing use that information to process that, and then infrastructure to distribute that to the car. That was the solutions we pursued.
Bong Young Song at Qualcomm. Essentially, I had the same question. So just to follow up, who are leading and who are lagging it? So for example, for M-City, collaboration with Verizon. So are we expecting the operators to put the roadside units or it should be driven by the city or local government? And of course, there are other players, operator, the government, and automakers and handset makers. So who are leading and who are lagging, and what would be the primary, force to get this going?
It's the industry that maybe we are not doing a good job convincing others about this. And it's a tough question. When you have RSU, maybe you rely, the big question you get is that who covers that? Is the city deploying that? Who pays for it and things like that? But on the other hand, the network part, maybe if it is a market-driven solution, the deployment might be easier. These questions, they still don't have any answer. And it's easy always to blame others, but others can blame you as well. So it's a chicken and egg situation currently. And there is no one to blame. I think the industry has to do a better job to make this happen. Yeah.
Okay, thank you very much. Thank you.